The topic of Karnaugh maps is ubiquitous in digital logic textbooks. What I wanted to do is talk a little bit about the history of Boolean algebra and how it has a corresponding visual representation, and then make some connections about where this falls in the context of modern digital design. So first of all, let's start with George Boole. Okay, George Boole, 1854. Almost certainly, he did not have computers in mind when he came up with Boolean algebra. Computers didn't even exist back in 1854. It was more likely that he was trying to use the rigor of mathematics to apply to human thought and logic. Okay, you can see how that would work, that we often think of things in terms of operations like ands and ors, and he was trying to come up with a generalization of regular algebra to apply to logic situations. Okay, several years later, Alan Marquand from Princeton came up with this idea of a logic diagram. So it was a grid layout for Boolean relationships, but again, well before the computer likely did not have digital logic gates in mind when he was talking about his graphical method for laying out logic diagrams. So then comes 1937, so quite a bit of time elapsed. So in 1937, Claude Shannon has probably the most famous master's thesis ever, and he described how Boolean algebra can be used for switching circuits meaning logic gates. So soon thereafter, but not all that soon, 1937 to 1952, Edward Veitch came up with a chart method for simplifying truth functions and basically rediscovering what Marquand did for switching circuits, applying it for switching circuits. So it's like the Claude Shannon equivalent for a visualization method for Boolean algebra. But there were some issues with the way that Veitch approached it, and so in 1953, so only a year later, Maurice Karnaugh from Bell Labs converged with the idea of a Karnaugh map. And so the nice thing about a Karnaugh map is it takes advantage of the way that you lay out the diagram so that you can exploit visual adjacency with logical adjacency, and we'll talk about that as we go through the theory of Karnaugh maps. Okay, so in the computational era, when we started applying this to computers, this was an important enough topic that you could actually come up with a software system that could do the ideas of implementing a Karnaugh map simplification or optimization. Okay, so there's this famous algorithm called Quine McCluskey. It's the first computer-based logic minimizer, and it was exhaustive and exact, and you knew if it gave you, you knew it was going to give you the right answer. The problem is it scales exponentially, and so beyond 10 variables, it's not very practical to use. All right, so Quine McCluskey, that's essentially, a computer algorithm to implement Karnaugh maps. So in 1984, it turns out that 10 variables, that's limiting, all right? And so sometimes we don't need a perfect solution if we can't find the perfect solution, if it's computationally inefficient to find the perfect solution. So you could use heuristics, things that are not exhaustive, things that are not guaranteed to give you the optimal circuit, but still cut through a lot of the redundancy and helps you make progress whenever you're needing to reduce the size of a digital logic circuit. So this is an important tool that's still in practice in a lot of electronic design applications today. And then in the modern era, from the 1990s to present, it turns out that a lot of the optimization is done within the development tools. So we're talking about how to use Verilog in this class, and we have, in many cases, like in the lab, we have a target piece of hardware in mind, and the target hardware has lookup tables that are 4 variable and 6 variable lookup tables. The fact that those exist means that Karnaugh maps that we do in this class, we typically keep things under 4 variables, are not really relevant. Okay, we don't need to do a Karnaugh map like minimization if we're going to put the full truth table into a LUT. All right, but that doesn't mean that Karnaugh maps are not useful. I think it's an important concept to learn what prime implicants are and groupings and how minimization happens, and the link back to Boolean algebra. So, like all digital logic courses, we talk a little bit about Karnaugh maps, but I don't want you to think that, oh, when I become a digital designer, I'm going to need to be able to solve Karnaugh maps. It's the idea behind solving Karnaugh maps that's important. You actually won't probably be doing Karnaugh maps other than to explain concepts from digital logic. All right, so it's still an important topic, and we're going to cover it, but I wanted to give you that historical background.